So, hello everyone. Welcome again to another class. As always, thanks for joining us today. I have a minor cold, so I think my voice could be not as good as always, and maybe I make additional mistakes or more mistakes than normal, but I will try to do my best. So just in case if you see that I say something that I didn't mean, just stop me and I will say it properly. Okay, so then today is day 11, and as we mentioned last week, so what we plan to do today is to learn how to estimate the height where the optical depth is unity for any wavelength position. If you remember, we did that for 500 nanometers, but after that was question, we said that we could do that for any wavelength position. So in particular, we're going to do it for the 850 nanometer spectral range that we are computing, that contains the calcium 8542 Armstrong line, plus the satellite lines that we included. And we're going to do that for 2D field of view from the enhanced network simulation that was computed with the Bifrost code. So I think it's something that I believe it's going to be interesting, and sometimes you would like to do it for this line, for a different simulation, or for the same simulation but different spectral lines, because as you will see, it provides some information about the line that is very intuitive and I think very useful. Okay, so then the process is going to be very simple. We start from the atmosphere, the Bifrost atmosphere that we transform in day 8. Remember that we downloaded the original snapshot and we just adapted to run them on arrange. And then we follow exactly the same script from day 9, where we computed the calcium full Stokes vector for a 2D field of view of the snapshot. And we will just add a minor variation for also computing the height where the optical depth is unity for a given spectral range. Okay, and then we will spend, I think, most of the class just to learning how to read and how to interpret and plot those results. Okay, so then before going to that, we, as I said in the last class, we have a miscellaneous section. In this case, is that Angel, he thoroughly revised a previous class, and he mentioned that the index they use for plotting temperature and magnetic field was not correct. So that at least log tau -5. So I already changed that and I've updated the programs that you have in Dropbox. The same for the labels on the inclination and azimuth. I think it said cows, and now I think it says correctly degrees. So this is also changed. And he also mentioned about some missing ideal procedures. I think I started this, but I forgot to say it in class. So in the main folder, so if you remember now, I always share with you a link, and this link has several folders inside. So it has SERP, RH, and then this side that I think is empty. And then I also included there an IDL folder where I'm including the IDL procedures that I in general use. So if you want to run some class and suddenly you don't have the ideal procedure for that class, just go to the online course and the ideal folder and just copy it from there. You don't need to check where I use it for the first time. So it's always there and I'm always updating it. Okay. And also thanks to Angel for checking this and giving very nice feedback. Also, I was looking, but just 5 minutes to Harsh issue, and I tried 2 runs. I remember, I think one was from day 4, class 4, and I tried that, and it was very simple configuration, and with full Stokes it worked. But then when I tried the complex configuration, the one we are using now with the satellite lines, calcium, and more wavelength points, there it seems that the code does not converge very well. So I don't know exactly what is the issue. So I will try to go from the case very simple to the complex one, adding things until I find what can be the issue. So far I cannot really tell you why it's not converging so well, but hopefully in the next class I will have some feedback regarding that. Okay, so then let's go to today's class. Oh, okay, there's a question. Yeah.
Hi.
Yes.
So I wanted to ask that so generally convergence iteration we set to 110 raised to power -3, right?
Yes.
So if suppose we set it to -10 raised to -2 or 10 raised to -1, so at what point do you think the results are really bad? I mean, what is the minimum acceptable of ITR limit criteria?
Yes. Yeah, that's a good question. So the idea is that I said that the second round didn't converge, and the idea is that the values were around 110 to the -2. And for me, I think this is not so good convergence for the calcium atom. I would say that the threshold usually can be 110 to the -3, 110 to the -3. I think that's a good threshold for the calcium atom. So to be sure that the accuracy of the non-empty solution is good.
Okay.
Okay.
Thank
good.
you.
Yeah. So then, as always, we have that I'm running some ideal scripts in RH, and this folder is called befrozen opacity. And this one is the one that I'm going to upload later on to Dropbox. And also you have day 11 that there's a presentation, the one we saw, and the figures, and also I will add some material later. Okay, but locally we are in this folder that is inside the RHF1D folder. So let's start with the synthesis of the lines. As I said, this is essentially day 9. So what I did is to keep everything as in day 9, but I added begin new and end new in some places where I really added new things. So I will go relatively slow, but just not entering details in most of the things until we reach a point where we have begin new, and there I will just enter in details. So just as a context, we loaded the transform atmosphere. We selected a smaller field of view. We plot this field of view just to have a reference. And then we computed the dimensions, the X and Y and the Z dimensions later for creating the Stokes profile on the array where we're going to save the Stokes profiles. And then we cut it, the atmosphere. So it's the same vertical domain, but we cut it the X and Y dimensions of the horizontal domain. And then we started creating arrays where we're going to save that information. So in the case of the optical depth vector, it's X and Y dimension times the vertical domain, because it's one-to-one to the geometrical height vector that we're using. And then if you remember, I mentioned that I was always, before doing the run, I was always selecting a spectral range of interest because I didn't want to save all the values. And in fact, last week I was doing a test with another atom. It was a potassium atom. And there, the number of wavelengths that are associated to non-interest transitions, so the one that you're going to use later, it's much larger. So I think depending on the atom you use, if you have an atom with a lot of levels and a lot of transitions, this will make more sense because you don't need to save like 1000 wavelength points if at the end you're going to use 200. So this was what I explained, but as I always said, you can always save it and then cut it later. So it's up to you to choose how you prefer to do it. One thing that I added here is just a comment, but it's related to the fact that now we are going to compute the height where the optical depth is unity for different wavelengths. And I'm not sure, I would like to hear hand feedback in this sense, but I believe in this case, the wavelength region that we are solving for the calcium line, we are solving it optimally. So I think it makes more sense to compute the height where optical depth is unity for that wavelength range than in other cases where the transition is not very well solved because we have just a few points. So I don't know if the opacity and the height where optical depth is unity for that points is accurate as in this case. So I think it may be better to just restrict ourselves to the spectral range that we are properly solving. Does it make sense what I said, Han, or any spectral point should have an accurate optical depth unity value associated?
Oh,
yes. Sorry.
sorry. Say that again.
So in this case, I'm going to compute the height where the optical depth is unity only for the calcium window that we know that we are solving it with a very good spectral sampling, Q-core and Q-win. So, and I think it's not so good to solve it, for example, for the calcium lines that we only have a few points, or for other transitions that we are not solving optimally. Is this correct, or it doesn't make any difference?
No, it shouldn't make, I don't think it should make much difference. Okay. I mean, if you don't sample a line well enough in your non-LTE grid, it basically means that your whole solution of all lines is suspicious, right? So not only in the line that you have fewer points. Non-LTE is really a tightly coupled problem where all the lines matter.
Yes. Okay. So then this is basically what I meant. So if you are going to compute the height where the optical depth is unity, is probably to restrict ourselves to those transitions that we are solving the best we can. So in this case, in the calcium 8542. Okay, so then we move, and again, this is the same as before, as a previous class. So we are going to save the Stokes profiles here in these arrays, and they are X, Y, and wavelength, and this wavelength is defined here. And then here is where we have new things that we are actually changing the script. So what we are going to do is to create an array that has X, Y, and wavelength dimension. And the idea is that for a fixed value of these 3 points, we will have a height, and that height will be where the optical depth is unity. So we will have that for each pixel, X and Y pixel, we will have a spectral range, and for each wavelength point of that spectral range, we will have a height value. Okay, we will go slowly later on that, but the idea is just that the dimension of the array that we are going to compute is X, Y, and wavelength. Then here it finished the new thing, so then it's the same as before. We save the continuum intensity at 500, and then as we saw, so we are going to create a loop that covers X and Y pixels, so all the pixels. And for each case, we prepare the atmosphere in the RH format, first the thermal part, and then the magnetic field, and then we just run RH, okay? And then we solve the ray at a given heliocentric angle, that in this case is mu equal 1, and then we read everything. And here I add begin new because I think we had some things that we read in the previous class, but now I added everything that I think is needed for computing the height where the optical depth is unity. So then here I think is just put these lines. I don't know, in Python I think maybe easier, but in IDL just put this line and I think it should work. And then we enter a loop. In this loop, what I'm going to compute is that for each specific X and Y pixel, we're going to compute the heights of where the optical depth is unity for the wavelength range of interest that we are computing. And the truth is that those lines are from Han from long ago, so I don't remember what is each thing, so maybe Han wants to add something. But basically we're using this routine, and we are, I don't remember what was Han.
well, the AS is active set, so that those are all the opacities that come from the
And continuum.
elements that you solved in detail for non-LTE.
Okay,
And the
this
C is the
continuous,
continuum.
the continuum.
Yes.
Okay, and then we call this tau1 ideal routine, putting as an input the geometrical height and the value from the previous sentence. And then we interpolate the results just using the index that comes from before. So I think just try to give it a try on this, and if you don't see it or you don't understand it, just let me know, or maybe Han, and then we will try to get through it. The important thing is that I did this in the past just for a few pixels, and in general I didn't have issues as far as I remember. But in this case, we had a lot of pixels. We have 230 times 230 pixels. So I started to see that the program was, or the script was stopping because we had some error like this one. And then I promised Han to send him an example of the error to check it, but I forgot. So what I did, and then I will try to work with Han to check what is happening, is just to go to this routine. And instead of saying the routine to stop if there is an issue, just I told it the routine to go through, because I assume that if, I don't know, 1% of the pixels are wrong, is still fine, because then we can remove them by hand. So I just went to the routine. I changed the name just to, so these are tau1.pro and tabin.pro are the original ones. They are in the RH library. So I created two new ones just to avoid mixing things with an index M. And I just did something very not sophisticated, and I commented the lines here just to allow the code to go through. So because I assume that it is like if the code abort for 1 pixel, you still want to have all the pixels, and then at the end you will just replace that pixel. So in this case, it's the same. So even if some pixel, for any reason, the computation is not correct, you just still want to go through, and then at the end you will clean the results. Okay. One thing though, and I think I mentioned here, yes. Ideally, I think the best thing, or what you should do if you have some time, is that instead of commenting this, add in some sentence that provides you some information. You can add it here, or you can add it in the program. So just to save which index give you some issues. So then later on, you know that, for example, I don't know, index 4450 and index 202, those index, those pixels, you need to replace them to the nearby one. In my case, I didn't do it, but I think it's a good exercise as a homework, as I said here. Okay, so then essentially we run those instructions from Han. We save vector that contains height values for the wavelength region, and then we save it here in the opacity array that is that for each pixel, it will have height value, okay? And then again, it finished the new part. So then this is more or less what we saw in the previous class. We are saving the optical depth values here, the continuum intensity, full Stokes vector. Then we're just printing to have an idea of how far from the beginning of the loop we are. And then here I put begin new just because we are saving a new array, but the rest is the same. Okay. So then we are going to, this is more or less what we had from the previous class. It's just that I added this. So then before going to check what we get, just as a summary, so we have an array that is a three-dimensional array, and it has the 2D dimension from the horizontal domain. And then the third dimension is the wavelength dimension. And for each wavelength point, we will have a height. And that height corresponds to the place where the optical depth is unity for that wavelength. Okay? So can I go to the next, or is there any questions so far? No? Okay, so then let's restore the values. Okay, so we restore the save file that we have computed. And the first thing, as we always do, is to try to check how the continuum intensity looks like. So in this case, I already have the figures here. So you can see that it looks very, very smooth. Okay, so then the computation, even if we added new things, in principle is the same. So it looks very nice. And then the second thing is, again, to check how the continuum looks. In this case, in the wing of the calcium line, that is the beginning of our Stokes profile. So the first index, as you remember, I just put it, I just cut it, the full RH computed wavelength range. I just cut it to the 850 window. So then the first index is the continuum at 850. And it looks okay. I will go back to these red lines in a second. Just one thing, if I remember correctly, I think in this plot, we had one bad pixel, but in this current computation, it's not there. So I put a note and I will check with Han because I don't know if I increased the maximum number of iterations, and then this means that that pixel that maybe had an issue before now it converged, or if there's another reason for the improvement. That it's always good to have it, but it's important to know why. So I will check if I change the iteration, but I think it was the same. Okay, but now let's continue and start with the new things. Okay, so we are going to we are going to plot the intensity profile for profiles for 2 pixels. Before that, I want to normalize them to the local continuum. That is something that we in generally do with SER, Desire, and most of the codes. So as you remember, we basically just compute the mean or the average value over the Stokes profile at the continuum intensity, because this is a quite some simulation. And then we just normalize all the profiles by this value. Okay. For the plot, I'm also reading the number of wavelength points, and you will see later why. And the idea is that it will be a 4-panel plot, so two columns and 2 rows. And in the first row, we will have the intensity profile from the corner of the field of view, and then the intensity profile from a network patch. That is the red line that you saw before. So let's go back. The idea is that I'm going to plot the intensity from this pixel in the left corner, and then the intensity profile from the pixel that is here where the 2 lines crosses. That is essentially the magnetic network patch. Okay. And the idea is that we will add in the bottom of this plot the height where the optical depth is unity for that specific pixel. Okay, so the wavelength range will be the same, but we will have height values. Okay, and as you can see, is the index 00 for the first part and the index 82 120. Okay, so let's check it, and then we can if you have any question, just let me know. So then, as I said, in the upper part, we have intensity profiles. We have the satellite photospheric lines, and then the calcium 8542 in the center. And as we said, this is quite sun. I think it's part of intergranule. And then we have here that this one was in the magnetic patch. It was a bright point. So then the continuum is higher, has higher intensity. And then the profile is also a bit different. Okay. So now if we go down and we plot the height where the optical depth is unity for the same pixel and for the same wavelength range, you can see that it has almost like an opposite behavior, where the continuum, it corresponds to lower layers. In general, in the quiet sun, it will be average to 0 kilometers, the 0 provided by the Vivino simulation. And then photospheric lines, they move up a bit. It depends on the photospheric line. Sometimes they go 100 to 200 or even until 300. And then you have the calcium line that goes really, really high. In this case, up to 1,500 kilometers. and then it goes down again, and then you have continuum again. Okay. Yes.
Carlos,
Yes.
regarding the height at which or where tau equals 0, or the optical depth is 1, height 0, right?
Yes.
It is maybe interesting to note that here at the calcium line in the infrared, you are very close to the maximum opacity, local maximum in the H minus opacity.
Yes.
So that you can expect the height to be slightly above 0 on average, because you are
affected.
if you know the curve of the H minus opacity, it has a maximum around here. So that's just an interesting solar fact, nothing to do with your calculation here.
Okay. Thank you. That's a good point. Yeah, that's true. And also because the continuum maybe at 850 nanometers is slightly different than, for example, 500 nanometers, right?
Exactly because of that.
Okay. Thank you. So then if we move to the other pixel, we have the same pattern. So continuum forms much lower than the line core, but as you can see, the line core and both the continuum, they have lower values of the optical depth, the height where the optical depth is unity. And in this case, I think it's essentially the presence of the magnetic field that is shifting from where the photons come from, and it's shifting it to deeper layers. And I think in this case is what we call the Wilson depression. So essentially, even if it's brighter in intensity, what could mean that, for example, it's a granule or intergranule, in this case it's brighter because of the magnetic field that is producing a bright point. And then both continuum and line core, they come from lower layers. Okay. So then I think, I hope this is interesting. So then let's move to an additional plot. I think this is for, the only thing, so this is what I mentioned. You can read it later slowly. But one thing that I didn't mention is that, as you saw, from quite sun with almost no magnetic field to a region with strong magnetic field that drops the formation height, it's around still 1,500 kilometers. And I think this is one of the reasons we in general assume that calcium 8542 forms around a low middle chromosphere, and it's around this value between 1,000 and 1,500 kilometers. Okay. But also always depends on the configuration. So in an umbra, it will be much different than, for example, in the quiet sun. Okay, so now let's go to spatial distribution. So in this case, we are going to do a slightly different plot. We are going to do a 2D plot of the spatial variations of the height where the optical depth is unity for a fixed wavelength. Okay, so then I have 3 panels. In the first one is index 0, that you can see that corresponds to this point, that is the continuum at 850. Then I picked one almost random, is the wing, but is not really exact value. So I just picked this one because it was around the wing, and the wavelength value is here. And then I picked the wavelength point or the wavelength index that corresponds to the rest wavelength of the calcium line core. So I call it line core, but as you know, there's some Doppler shift in the simulation. So the line core is not exactly at that point, but just for keeping it simple, I just picked the rest wavelength and I plotted here. Okay. So then let's check that one. This one is this one. Okay. Then let's make it bigger. Okay, so if we start with the spatial distribution for all the pixels of the height where the optical depth is unity for the continuum at 850 nanometers, you can see that it looks more or less like granulation. So you have that granules, they have a higher height, and intergranules, they have slightly lower height. But sometimes it depends on where you are looking at. And interestingly, as we saw before, the bright points that we have in the intensity that correspond to strong concentrations of magnetic field are very dark in this color plot. That essentially means that they form much lower than the other areas. But basically we have the imprint of the granulation pattern. Okay, if we move to a bit closer to the line core of the calcium line, things are a bit different. I think the word I use is dynamic. I'm not sure if it's proper here, but just try to follow what I mean. And the idea is that some of the structures that you see here, for example, this granule, they still seem to be here, but in general, everything start to wash out, and we are moving around 200 and 500 kilometers. So as we are getting close to the central part of the line, we are moving at higher layers. Still, regions where the photospheric magnetic field is strong, they still show a height where the optical depth is unity lower than the rest. But I think it's just interesting to see how it looks. And then finally, if we move to the height where the optical depth is unity for the line core wavelength position, then as before, it looks very nice. It looks like the intensity, line core intensity. So we have that there are some magnetic field concentrations and there are some kind of threads moving away from it. And in this case, we see that some threads, they are with a white color, indicating that they form higher than other ones. And we still see the shadow of what the photospheric magnetic field were more or less located, and they still show lower heights there. But essentially, I would say that this is very interesting to see how the optical depth, the height where the optical depth is unity, is changing with the shape of the atmosphere. Okay. So then I think I would like to have 2 more plots. I think I covered everything. So then I would like to show you how we can do a 2D plot to also visualize the previous figure, but in a different way, something that I've done in some works in the past that I mentioned in the last class. So then in this case, what we're going to do is to cut a slice of the simulation. So it will be a horizontal domain, could be X or Y, it depends on you, and then height. So then we will be able to see how the line or the height where the optical depth is unity is changing and how it moves to different layers and move down. So similar to before, but in a different way. And also a way that I think it's easier to make comparison with other lines, spectral lines. So you can add them on top of each other and then see if they follow the same pattern or if they form lower or higher. Okay. So then for that, we need the atmosphere that we were not using it so far. And I think the simplest way is to just load the atmosphere that we transformed. In this case, I'm going to do just 2 plots, one for temperature and one for the field strength. So I just, I'm going to use only those atmospheric parameters. We cut them to the specific field of view that we are using, and we need to reverse it just to see it in a more natural way. So then what I'm going to do is to store the reverse values. I'm calling them now temperature. Before it was temperature reverse, I think was the meaning of this index or the character, and then field strength. So we just run, I just defined them equally to the other, but just multiplying by 0. And then in each, so we run a loop for each pixel. And then for each pixel, we just reverse the temperature and the field strength. Okay. And for the plot, we need also the values of the geometrical height. So I reverse the original one. And also we need the points. Okay. So then let's start here. This is the plot for the temperature. So we have a 2D, a 2D plot of the temperature. And in this case, if you remember, it was X, Y, and Z. So I'm fixing Y. So it's a horizontal cut of the simulation. And in fact, is this horizontal cut. Okay. So I'm going to plot this the domain, horizontal domain, and all the different atmospheric layers and temperature with height. Okay. And I picked this one because you have a lot of white sand, you have granules, you have intergranules, and also it's crossing the concentration of the magnetic field here, here, and here. Okay, so we will see several variations, and some of them related to thermal changes or other changes in atmospheric parameters, and others related with the presence of the magnetic field. Okay, so then I will just plot that. Let me show you the background, and then I will explain you how we add a plot on top of that. So then this background is what we saw. So the horizontal domain, this x-axis, is the line that was crossing the field of view. Sorry, my voice is getting lower and lower. And then the y-axis here is actually the geometrical height. Okay, so each value in this direction are different atmospheric layers. Okay, so before getting to it, yes, let's check how we plot these different color lines and what they mean. So what I did is, let's try to see, because we have mainly one spectral line. So let's see how it looks, the continuum, the wing that we saw before, and the line core intensity. So then blue is the index 0, that is the continuum. Orange is the wing, so then it's a bit above, so it's middle photosphere. And then red will be the line core, rest wavelength. Okay, so I'm just doing an overplot of this, but in this case, just if you are going to do it in IDL, or maybe it's also helpful if you're doing in Python, as we are defining the x-axis as with the original dimensions of the simulation, so it's in megameters, I need to create also an abscissas axis with this dimension. So then what I'm just creating is a vector that is increasing one by one, is starting on the initial value of our selected field of view, and then I'm multiplying this for the scale that in this case is 48 kilometers, but is in megameters, so it's 48 times -3. I think is in the beginning of the script. So essentially, I'm just making this to have it in the same format. Okay, so let's go back. Sorry for just moving back and forward. So then what we said is blue is continuum, orange is the wing of the line, and red is the line core and rest wavelength. Okay, so then you can see that the lines are not straight, and this is because there's variation, spatial variation between pixel to pixel. And you can see in the case of the continuum, we are basically following what I would say is the transition or the interface between the convection zone, that is probably this one here, and the rest of the atmosphere, in this case the photosphere, and then above that chromosphere and transition region. Then we have that it's following very well this white zone, but then it goes down here and also here and here, and this is just that the magnetic field there is strong. You can see also the temperature drops. I will show you later the magnetic field, and you will see that it's very correlated. But it's basically that. So this is basically what we would have more or less with the optical depth unity at 500 nanometers. Okay, then if we go closer to the line core, in this case the wing, we have in average, as we saw, around 500 kilometers. But again, we have fluctuations. In some cases, they are correlated with the presence of the magnetic field. And in other cases, they are related with changes on temperature or maybe density. So it's something that is it's changing with different pixels. Okay, and then we have the red line, that is the line core. It forms much higher, around 1,500 kilometers. It drops in some cases, but in other cases, for example, in this case, temperature is much lower than the surrounding. It goes up again. So So then you expect large variations, maybe 500 kilometers variation of the line core intensity. Sorry, the height where the optical depth is unity for the line core of the calcium 8542 line. I think two things as a note from this plot. The first one is that you see I use log scale because we are covering from the convection zone to part of the transition region. So they are the changes on temperature are really, really high. So in order to be able to see something here, I was using log scale, and also I saturated everything from these layers. So it doesn't look so nice. And in general, I would try to cut a bit more of this just to remove all these saturated areas. But in this case, I wanted to show you that if you remember, I think Alberto was the one asking the question, how far should we go when cutting the atmosphere for computing the calcium 8542? And in this case, if you remember, we picked to cut the atmosphere up to 2,500 kilometers. And you can see that in this case, the line is moving up and down, but in general, it's always below 1,700 kilometers or something like that. So this is an indication that if you move around those heights, you are probably okay for computing the line. But as I said, maybe going to 3,000 or maybe up to 4,000 is not so bad. But in general, here we can say that we are probably in the safe side.
Yeah, just remember that you also have to represent the H and K lines properly if you do calcium non-LTE. So you might want to look at the line core optical depth unity line for those two lines if you want to see where you can cut safely.
Yes, that's true. And those two are they from higher, so you can expect probably 2,000 or a bit more. Yeah.
Yes.
That's a good note. I think that's.
So okay. Sorry. So
yes.
My question always was intended to clarify. I mean, in addition to what you said, my question it was only trying to understand if we have to include a little bit higher atmosphere to represent the physics that is happening there in terms of density, opacities, and these things that might be have an effect in these lines, even if this is not directly these lines that you are computing, the other lines, I mean, the other elements. So that was a little bit my question. I understand that exactly what you said. You expect the formation region of this line around no maximum than 2,000 or 2,500, let's say, and then you say, okay, I can crop here because of that. But if I want to consider maybe something is happening a little bit higher and is affecting to the general variables in the atmosphere, I don't know. It was just a.
Well, but this is already. There's no feedback of this calculation on the MHD of the atmosphere, right? So you only, since you're taking a snapshot in time, you only have to concern yourself about the radiative transfer effects, not about the physical effects of material that is higher up, because that's already done.
Computed. Yeah.
Yes.
Okay.
Yes.
Yeah, that makes sense.
Yes.
Thank you.
Yes. I think, Alberto, what you are saying it's an interesting question. But my impression is that if something happens above, you will have a perturbed atmosphere below. And that perturbed atmosphere that you're using is already taking into account what is happening above.
Yeah.
But you don't need that one for the computation of the spectral line.
Okay. Thank you.
Okay. Yep. Okay. So then I think now we can move to the magnetic field. Yes. So in this case, we're going to do the same, but just replacing the background with the magnetic field. And it's this one. Okay. So then, as you see, we have the same lines and they are varying in the same way. But in this case, you can see that, of course, as we said or we assume, when we have these tips in the, for example, in the continuum, they are in general related to a concentration of the magnetic field. So you can see in all the cases this happens. It is true that then it's more difficult for the calcium line to directly associate the perturbations to these changes. It's true that it's lower here, but then you have like variations here that is not so clear that they are directly related to the magnetic field. So in the chromosphere, I think it's a bit more delicate to understand the direct relation between an atmospheric parameter and a change. But essentially, we see that both magnetic field and temperature, they can modify a lot the height where the optical depth is unity. Okay. So then I think that's all for today. Yes, yes. And now I would like to do a summary. And the idea is, if you remember, we repeat the same synthesis, and doing that, we also computed the height where the optical depth is unity. So with the same script, we are doing more things than before. And the idea is that what we are representing in the current plots is what we usually can call as the height of formation, although we should be careful about that term. And I think it's very useful to have it. And also it would be nice if you add different lines in the previous plot, for example, spectral lines, like for example, I don't know, sodium, potassium, another calcium line or magnesium. So lines that we use, you can add them to those plots. And I think it's very intuitive to see differences. But my advice is that take that just as an initial step on understanding how the spectral lines behave, and also for comparing them between each other. But the idea is that even if you have lines, spectral lines, that they have a similar behavior or height of formation, they can answer or respond very differently to changes on the atmospheric parameters. So one could be much more sensitive to the magnetic field. One could see the temperature changes with large changes on the spectral line, or other maybe cannot change, or maybe doesn't show changes. So what I mean is that if you really want to know more about the spectral lines that you are going to use and what you can expect from it, we need to take a step forward, a step farther from this. And so this is good to know more or less where the line core, for example, formed, but we need to compute the sensitivity of different spectral lines to changes on the atmospheric parameters. And this is essentially what we're going to do in the next class. We're going to compute the response functions. If you remember from the third class, they give us an idea of if I change an atmospheric parameter, for example, magnetic field, at a given height, does the Stokes profile see those differences or not? If they see it, then we can assume that the spectral line that we are using is sensitive to those changes at those heights. And if there's no change, then we assume that that line is not going to help us, in principle, to inferring the atmospheric parameters, at least at those heights. So then in next class, we will learn how to do this, and we will move a step forward to understand how the calcium line can give us information of the photosphere and the chromosphere. Okay, so then before going back to the presentation, is there any question related with today's script or tutorial? No? Okay.
I have a very basic question, and it might be too basic. If you were to try and explain to someone who has a fairly basic understanding of physics why a given line will have a different height of formation than another line, even if every atmospheric parameter is the same, what would you say?
Han, do you want to do it with a very accurate definition, or shall I try? I think it's better if you do it.
Yeah, well, that's hard to.
Maybe can I try, Han, and then you correct
Yeah,
me?
sure. Yeah.
So I think I want to start with the basics of photons and telling that photons come from the optical surface, but on the way here they interact with matter. And different, so you have that they can interact with different atoms on their way here. And those atoms are not located in the same atmospheric layers and with the same concentration. So when we see a spectral line, for example, an absorption, is related with the interaction of the photon with that atom. And the idea is that those atoms, as they are different, located at different height, and they behave differently. So we have that the height of formation, it can be different from one spectral line to the other. I think maybe Han, you can build on that. And
yeah, well, I think maybe the easiest to understand analogy, maybe if you have water that is not quite clear, and the more stuff there is in the water, the less deep you can see, right? So and this is true for in a similar way. Spectral lines add opacity, add absorption and emission. So if there's more stuff in the water, you can't see as deep, so you don't get information from. You only get information from higher layers in the water. I think that may be the easiest way people can understand the effect.
Yes, and the difference between lines, I think, is just that. So how the photons interact with the atom itself. So they have a different interaction and a different type of absorption, and also the concentration of the atoms is different between layers.
So if I make it even more nitpicky, you have the same species, which is an iron 1 atom, and you have one transition which gives rise to the infrared iron lines and another one which gives rise to a visible line. You're saying that there are atoms that are susceptible to receiving those photons and undergoing that transition at a different height than the other?
No, it's just that the chance of an atom interacting with a photon is higher in some lines than it is in others. So it really is only the opacity that matters in this case, right? It is that you have a bigger chance of a photon being absorbed or not.
Yes. Does it help, Ryan? Or
it's really the strength of the interaction between the photon and the material.
Yes.
Okay. Is there a physical parameter which characterizes that?
Yeah, the line strength, basically.
Okay.
So how deep is the line?
It's the line strength times the number of particles in the lower level.
Okay. So maybe before going to Harsh, so Ryan, is it helpful, or do you want that we elaborate?
Yes, thank you for that explanation.
Yes. In my case, I was talking about different atom species.
Yeah.
So or ionization levels. So for example, calcium-2, it's only present in the chromosphere. You don't have it in the photosphere. So when you have an absorption, it essentially comes from where the atom is.
Yeah.
And in your case, you are talking about the same atom, but the transition, so the photon that is emitted, it corresponds to a different transition inside the atom. So different levels are populated, and when you have a cascade or something, we can do it in more elaborate way. But the idea is that the photons, they come from different transitions, and what Han is saying is that you have a probability of that photon emitted or not based on the strength of the line, and this can make. Yes. So
thank you. I just wanted to make sure I'm not taking anything for granted.
No, it's fine. I think it's a good question. Yeah.
Carlos, I have to go to another meeting.
Okay.
So
I'm almost finishing. So
okay.
Thank you. Bye.
Bye,
See you.
Yeah.
Harsh, do you want to add something?
I just wanted to just ask, like what Ryan asked. So basically, does it not depend on temperature? Like, I mean, if what height? I mean, I may be wrong. I just want to confirm that. Suppose I want to know at what height this line will be formed. Would I not check the lower level population electron volt? I mean, the energy level, and then check the corresponding temperature for that electron volt, and at what height that temperature will come, most likely around that height I will find that line. Is that correct, or is it false?
I think you need to, for example, in this case, what we have is that you need to take into account not only temperature, but in general all the atmosphere, because temperature changes can also affect the density. and also you can have a magnetic field. So I think the best thing is to include a complex atmosphere, like in this case, where you have multiple variations, cooler, hotter, magnetic field, no magnetic field, and they are estimate an average. But the truth is that it depends on all the atmospheric parameters, not only temperature, but also magnetic field, and also the other parameters are in general coupled with temperature. So I would say that the best thing is to do it like we did it today. So you have the full atmosphere, you provide it to RH, and then RH internally takes into account everything to compute the background opacities, and then to compute the opacity of the line itself. And from there, you will have the height where the opacity or the optical depth is unity.
All right.
Okay. Okay.
Thank you.
Thank you. Yeah. Dato, yes. Go ahead, please.
Carlos, just
Yes.
very quick question.
Yes.
So I guess with pretty much the same way, we can calculate optical depths as a function of height, not just optical depths not just the position of tau equal 1 layer, but
Yes.
the optical depths as a function of height with for each pixels, right?
Yes.
Should not be a problem, right? Because we have geometrical depths from
Yes.
Bifrost, we have
Yes.
opacity from RH, and yeah.
Yes, the truth is that I haven't done that, but I guess you have it from this read opacity. So probably
Yes.
from here, somehow you can have it, because I think what we are doing here is just computing where this chi total it has tau equal 1. So probably using this routine, or maybe Han knows the way, you probably have the full height variation of the optical depth for each wavelength point.
Yeah,
I think
okay.
I think this is, so I'm certain that this is included in the code, and probably it's going to be straightforward to ask the code to provide that value. But the truth is that I haven't done it, so maybe we check with Han.
Okay.
Okay.
Thank you.
Yeah, thank you. I can just take note of that. Opacity. Okay, so then just let me go back before my voice completely falls and I cannot speak anymore. So then homework, as always, very easy. Try to run the example. If you use IDL, so trying to follow the script and run it and check that everything works. And then as an extra, as I said, I just remove the option of stopping the run if it doesn't provide the best value, because I wanted to run for the pixels and I knew that it was like 0.1% of the pixels. But I think it's good to ask the code that I want to know where we had problems, so then I can just replace those pixels for the nearby ones and then be sure that all the pixels are as good as possible. Okay. So then next class, as we said, we are going to learn how to compute response functions numerically. We knew how to do it analytically with SER, but this was in LTE. Computing response functions fully in analytical mode for non-LTE, it's really, really, really difficult. There are some reference that I will try to mention next week. But the simplest way and straightforward is to do it numerically. It's time consuming, but it's relatively easy to do. So then I will show you, I will follow most of the explanation that you can see in this publication. And then I will try to make the plots that I show, for example, in 2017 in this work, where you see the 2D variation of all the lines and I compare with between different calcium lines and things like that. But essentially, I will show you how to compute numerically and response function with RH. Okay, so then, yes, this is what I said. So any last question before? Oh, yes, I'm recording, sorry. I thought that it was not recorded. Sorry. Any last question before I wish you a nice weekend? No? Okay, sorry again. This class was a bit, I think, probably slower than usual, but as I said, I have a bit cold, but I hope it was helpful. And as always, if you have any questions, just let me know. And next class is in 2 weeks, November 12th. And I hope you enjoy the weekend and also have a happy Halloween. Okay. So thanks a lot, everyone. And
Thank you, Carlos.
I hope to see you in 2 weeks.
Thank you, Carlos. Happy Halloween.
Thank you,
Happy
Carlos.
Halloween.
Bye bye.
Bye.
Thank
See
you. Bye.
Have a nice weekend. Bye.
Bye.
See
Bye.
you.
Bye.
Bye.